So if you have two matrices, so you see my notations, it's very short writing, but you can figure out every bit of the information about the matrices from this notation. You know which letter I used to denote the entries. You know how many rows and columns I have. So when you add two matrices and you use this regular plus sign for that, if you have two matrices and they are, you see, of identical size, they all come from the same space Mn. When you add them, you just add the corresponding entries. You see how efficient the notation is. If you imagine writing this big table of numbers on my first slide, it would take so much space I couldn't fit it on the screen. But with this notation, it all fits and every piece of the information is here. You just have to be able to extract it. When you scale a matrix, you scale every entry with that number. Well, subtraction is not an independent operation, but I often mention that. When you subtract two matrices, you subtract, again, in a pure entry way. I have two examples here. Actually, maybe three examples. So I have two matrices, A and B, one of them like this. No, actually, I have three matrices. It's my B matrix. And here's my C matrix. I'll give you some time to copy that. I will have more examples with the operations of matrices. I will use these three examples, so you don't need to copy them all the time. So of these three, we'll go through all of the examples, A, B, and C. These are 3 times 3 matrices. You see, that's why I said something like this. When you write numbers, I mean, when you use here letters, you can write Mn. But when you write actual numbers here, it's more conventional to put a comma in between, because otherwise it will be M33. It will be confusing writing. That's why when you write numbers, people normally put comma there to see what's for the first index, what's for the second index. So if you triple, for instance, that's a very simple example. If you triple your A matrix, you triple every entry here. Look at this. If I take this box, here's my first entry. Here's my first entry here. First, here, 3 is a triple of 1. 6 is a triple of 2. 9 is a triple of 3. And the same rule goes across all of the entries. You see, you triple your entries. All of the entries are tripled. -1 times 3 is -3, here and here. This resembles vectors a lot. You just multiply every entry by 3. If you add two, for instance, A and B, they are of compatible size. A and B of compatible size, you can add them. Look at this. Is the first entry here, which is 6, and that is 1 plus 5. Nice, isn't it? Here's a 5, which is 2 plus 3. Here's a 12. Nice trick, I like it, huh? There's a 12, which is 9 plus 3. So you do this on the per entry way. 7 is 9 and -2. All of them like just entry by entry. As long as they have compatible size, you're good to go. Oh, beauty. 5 plus -6 is -1. Good. Well, I also have here the value for the negative. I'll open it. I'm not going to take you through that. It's just you do this again on the per entry way. You subtract the corresponding entries. If you ask the question, what will be B plus C? If I ask you the question, what will be the B plus C? The answer to that question will be not defined, because B and C of different size, and you can't do much about that. You just say it's not defined. Like with any other operations we discussed with you, these linear operations with matrices, and when I say linear, it's two operations, addition and scaling. They have this regular set of properties, quite expectable set of properties. Again, like I said, no surprises here. They resemble vectors a lot. I have a few of them at the bottom of this slide. I have a few of them here at the bottom of this slide. basic properties of addition of matrices or linear operation with matrices. If I have now 3 matrices and 2 scalars of compatible size, see, identical size for all 3 matrices, we have quite expectable set of properties for the linear operations. We have what we call commutative law, which means that you can add matrices in any way you wish, A plus B or B plus A. You have this associative law, which looks like this, which means you can put the brackets when you add matrices, again, in any way you wish. It is less expectable, well, it is still expectable, but probably less obvious, is that like with the vectors or with numbers, addition of matrices has this special element we call 0. It's the element, the distinguished property of that element is that if you add this element to any other element, nothing will change. What will play this role in case of matrices? What will play the role of 0 in case of addition with matrices? What's your intuition tells you? With numbers, we have a number 0. You add the 0 to any other number doesn't change. We have to have something similar with matrices. What will take the role of a 0 in case of matrices? It's just a name. We will call that element 0 matrix, but what it is? It's the matrix with all elements 0. It's quite expectable guess. Yes, it is. But the interesting thing is we have many of those, right? For different sides of for different classes of matrices, for matrices of different size, we have different 0 matrices. Unlike numbers, we have lots of zeros here, lots of candidates for the zeros. So here it is. And that sometimes actually it is instructive to distinguish this. So you see, I index my 0 matrices with the corresponding size of the matrix. We have this special element, 0 matrix, which is basically the matrix which is filled with zeros across every entry. And the property of this is that if you add this to any other matrix, the matrix will not change. Keep this in mind. For different matrices, you will need to produce different 0 matrices. For instance, the C matrix from the example above, you don't have to copy that. That's the same C matrix it was on the previous slide. This is a matrix of size 3 times 2. I have to use a special 0 matrix, O, 3, 2. And then, if I use it, if I add this matrix to my C, that will not change my C. There are a few other laws, again, quite expectable laws with the additional scalar multiplication of matrices. For instance, you have the scalar distributive law, which says when you multiply sum by scalar, you can distribute this scalar across the individual terms. Scalar distributive law. There is a matrix distributive law of similar nature. Look at this. If you multiply a sum of 2 scalars by a matrix, you can distribute the matrix across the scalars. Quite expectable ones. Do I have any other? Well, you have that if you multiply the matrix with the unity, number 1, matrix doesn't change. If you multiply a matrix by a 0 scalar, you will end up with the corresponding 0 matrix.